Hi, I'm Becca. I'm here with my colleague Louise. We're from a Canadian company called Mission Control. And we're going to tell you a bit about what our team has been doing for testing approaches for machine learning payloads on some past missions, as well as a couple of upcoming missions. Maybe no clicker, that's all right.
Okay, so that was frozen. There we go. Now
Okay,
you're good.
thank you. Yeah. So what I'll cover today, I'll tell you a bit about who we are and the missions that are going to use these approaches. I'll talk a bit about our model development approach. It's connected with the way we test things, of course. Then I'll go through some test methods. A lot of these are relatively generic to, I think, data processing payloads. There's just some choices around the types of data we're using and that kind of thing that are specific to machine learning. Then I'll hand it over to Luis to talk about test implementation and conclusions. So mission control, we primarily do software for spacecraft, about anywhere you can send spacecraft. We're interested in doing it. Historically, we've done a lot of things with rovers, especially lunar rovers, software, mission operations, bunch of R&D, interesting analog testing, stuff like that. But for the last couple of years, we've started getting into satellites, robotic arms, other kinds of assets like that. So one mission and model that really informed a lot of the work that we did today is our MoonNet lunar terrain segmentation model. This flew on the iSpace M1 mission. That was one of the ones that hard landed, unfortunately, but we got to do a lot of our development. I won't talk about this anymore right now because Luis and I got to talk about it at FSW 2023. So two upcoming missions. The first one I want to talk about that we're using some of these approaches on is our Cube rover joint lunar mission with Astrobotic. So we're going to be using Spacefarer, which is a different part of our team's mission operation software to actually operate Cube rover. And then we also have a lunar terrain segmentation model on board Cube rover, bit of a successor to our MoonNet. So this is going to be a really exciting one coming up. And then the second one I want to talk about is a satellite mission. It's an Earth observation satellite with an optical payload, where we're going to really be using it as our AI lab in space for a minimum of a year. This is launching later this year. And the main thing we are interested in, the main experiment we want to run, is long duration like AI behavior. So we want to take the same model, we want to try updating it over time for over 6 months, up to a year, to understand the way that concept drift and making these multiple updates over time, as well as cumulative radiation effects, might be different for machine learning models versus traditional flight software. We're not totally sure what we're going to find out. That's part of the fun of doing the experiment. But that's the primary thing we want to do with this platform. We do have time and space to run other things. So we're also taking expressions of interest from third parties who want to run their own models or other software tools as well. So it's pretty exciting. I'll get now more into how we tend to develop models. Our team is pretty small. It's a mixture of a few AI specialists and flight software engineers, just on the team that actually develops the models and the related software. So we tend to design the models concurrently with both the flight and ground software that's related to them. I think this is actually a big benefit because you tend to figure out a lot of things along the way, and it's a way we can move quite quickly. So I've included our model lifecycle, very high level diagram on the right there. Basically, we start with a bunch of development phases. I'll get into a bit more what those look like. But then we take our model, after archiving it and doing a bunch of cataloging of its information, we'll take it into deployment production. So that's on board for us, that's rovers or satellites right now. Then data from there, so both the input data passed to the satellite and our model results, as much as we can, we bring down. That's fed into operations and a model monitoring system. And from there, it's actually fed back into development so that we can use it to retrain new models. So I think that's kind of all I wanted to say about that. Part of what we're going to be doing in persistence is just collecting a lot of service history for all of this and really trying to make as many updates as we can, focusing on making, maybe a model update a week for multiple models over this time span of a year. So zooming in on our development phases, we used to have less, I would say. We used to have kind of just one big common thing, and maybe it would be thrown out from mission to mission. Maybe we try to persist little bits in between. It's a bit more ad hoc. We've recently split into having this like R&D sandbox, as I call it. In there, the AI specialists are lead. They have free reign. They can go and create a bunch of Jupyter notebooks. They can go and pull in a bunch of code from different papers and move pretty fast there. Once they've found a model or some data sets, some other features that they're interested in, they can make a feature request into our core development. This piece is common mission to mission. And in here, we do a combination of some more like formal retraining. We have higher code standards. We've really actually leaned into typed Python for the training code, so that's being wrapped around the PyTorch and TensorFlow frameworks. And for the missions we're doing so far, we train in PyTorch or TensorFlow, and then for all of them, we're converting to ONNX, and then doing some optimization and executing with a combination of what we call Spacefarer AI, our set of tools we use to do that kind of thing, with an ONNX runtime backend for what we've been doing for these missions. From there, we go into staging. This is sort of the formal process of a final set of training of the model, setting the clean environment on a dedicated workstation. We do a bunch of cataloging. We make these model cards, which are a really good way to document all the info about your model, as well as any caveats about the ways it should and shouldn't be used. And we've been using these like model acceptance, just YAML spec files that are directly connected to our requirements. We feed those right into hardware in the loop testing. That's been something that's been working pretty great. So one thing I wanted to highlight before getting into testing, a big theme for us in the last couple of years is just getting consistency in our model performance, or if we have discrepancies, making sure those are discrepancies we understand, and ideally, they're actually improvements in the model. So I've listed a few of the things we have started doing on this slide to encourage consistency. One I wanted to shout out here that I've really been enjoying is that we've started using Python bindings of the processing utilities in our payload code. We expose bindings of the payload code directly to be used in that core development block while we're training the models. This maybe seems like a slightly strange thing to do, but we have found a surprising number of bugs result from image reading and writing, pre-processing, different things like normalization, just from flicking between different versions of common libraries or different libraries between Python and C. We used to get a whole onslaught of bugs there. We don't get any anymore, so that's been really great for me. Yeah, I think that's the main thing I wanted to say here. The other thing that I've also been enjoying is the model metadata file. This is like a very simple file that is just always shipped with the model. Contains a pointer to the weights, contains all the information that can't be inferred from the weights. Saves you from having to dig between software in a bunch of different places to check that you have things like the class order right, stuff like that. So we use the exact same file for execution on ground, flight, and in our test bed. That's been pretty great. So actually getting into some of the test methods, high-level overview of the test types. We have the vanilla ones you'd expect. So our unit and integration tests. The only thing that's different in our regime is that the data we're using in integration tests, it's not just randomly generated. We also use some that is sampled from the model test set. So this is a set that is held out of the data that was used to train the model. And we also use the most recent mission data that we have, or if it hasn't started operating yet, just the highest fidelity data that we can get. We also have some onboard model verification tests. Right now, these are relatively simple, just testing for predictable outputs on test inputs that are cheap to run. But as part of the persistence mission, we're gonna try out a bunch of other things there. It's gonna be a lot of fun. And then we have these model comparison tests, which are really about verifying that consistency, which I'll get into a little bit. So we have these model comparison tests. What I'm showing here is I'm using segmentation masks. They're a little bit prettier than classification outputs. And I have a bunch of segmentation masks along the bottom. These are all from, the same set of weights, so the same model. And this is the model sort of going through our phases of development. We test between sandbox and development. We expect there might be some discrepancies there because the implementation has changed. We've gone from sort of the research level code implementation to one that has a lot more test coverage and stringent quality standards. So usually we're seeing an improvement there, bug fixes, things like that. Then within the core, we're testing between the execution of the model with the high-level frameworks and then the converted version. And we generally test the converted version actually with the payload code as well, because we might as well at that point. And then between core and staging, what's changing is the target hardware. So this is where we start testing on dev boards and also the architecture. We do the cross-compilation there. So we want basically equality on that one. It's a fuzzy equality depending on some precision things. And then finally, this is my final slide before I hand over to Luis, we have the model comparison tests we really care about. So the ones between the model we staged, the model we have on board, and then this model monitoring is basically a copy of the model we've staged, but we're running it on fresh data that's coming down from the satellite. And we really want these to agree. Reasons they might disagree, things like corruption of the model file when it was uplinked, or radiation effects, things like that. So I'm kind of interested to see if we are getting discrepancies of this over our mission. Yeah, so the other thing I wanted to show here is just when we're getting the new data, we get a new image, we can create a new segmentation mask, and we're really doing that in both places. So this is the testing that we have ended up finding useful. Maybe it seems like a lot of testing. I feel like it looks like more on the slides. All of it is pretty automated, and we found some test setups that make it pretty easy to add new test cases, especially introduce new test data. So I will hand it over to Luis to talk about that part.
Hello, yeah, I'm Luis. I'm going to talk a little bit about how we actually implement these tests, especially when we move from a testing on a workstation going to some target hardware. So we're using an approach called behavior-driven development, or BDD. Who here is familiar with BDD? Yeah, so yeah, I'll give it a brief overview about it. But that's a good, that sentence from Wikipedia, I think summarizes it really well. We use a domain-specific language to describe the expected behavior of our application. And this is really tied to, it has its roots on agile software development, where we're iterating very quickly and having some automated testing framework running on some CI/CD setup. So the tooling we've been using are just some tools like that are worth mentioning here. The Cucumber is like a very probably the most popular BDD framework out there. It supports a bunch of languages. This is the language you write your tests in. It's not the domain-specific language, it's just a conventional one. And Cucumber defines a domain-specific language called Gherkin, and that's the one we use. But in our case, we use the framework called Behave, which is kind of a copy of Cucumber, but it's for Python because we write our tests in Python. So yeah, this is like what a Gherkin file looks like. You usually have, when you're adding a feature to your application, you create what's called a feature file. And you have a bunch of scenarios in that feature file that describe the behavior of our application. Here we have two. And here I have an example, a very simple example of a stack. So you have one scenario to create an empty stack and to push an element into the stack. So scenarios are basically test cases. And each test case or each scenario has it's a sequence of steps, and there are three types of them. There's a given, when, and then steps. So givens basically where you set up the test case, the test state, initial state. And then the when is where you actually do the call the whatever you're testing. So if it's a function, you're actually calling the function there, or an API endpoint, for example. And then the then step is where you make assertions about the results. So where you actually verify that the behavior is what you expect it to be. So this is a scenario outline. It's just a template basically. You can have these template scenarios where you have variables, like in this case, n, which is the size of the stack. So if you want to try, in this case, like to remove an element from the stack with stacks of different sizes and test, all the edge cases, you can have these scenario examples. So you can have a table at the end with the stack size you want to test, and then you plug that into your scenario. So if you look at this example here, basically you have these and steps. So there's given and is just like, you're just repeating the given step. So you're setting up, like, I have a stack with a bunch of elements. I state that the element E is on top of the stack. And then when you call a function to remove it, so in the then step, we're going to check that the expected size is n-1, and that the removed element is actually E. And how these steps needs to be implemented. So in Python, this is what it looks like. So you have these, you import behave, and then you have a few annotations to create these steps. So you have given, at when, and at then. So you put the name of the step there. And then you have a function that accepts a context as a parameter. This is your text context. It's carried over from one step to the next. And then it's usually reset at the beginning of the scenario. And then you just operate on top of the stack. So in this case, when you create a stack, for example, in a given step, your line here. So yeah, so you create a stack there, you add it to the context, and then at the when step, you're gonna add an element. So you create an element calling your code that creates the element, you add it to the context, you call the function, that's where the test happens when you do the push. And you add that element, and then the then step, you're gonna call the top, check the top of the stack to see if the element's there. So it's a very simple scenario just to show you what the kind of, how this whole thing works. So this is an example of the type of test we're doing. Again, a simplified scenario so imagine you have an image classifier, for example. This is what we call an application level test. You have your unit test where you're testing a bunch of components. So you then put those components together and you're gonna have an application here. You can imagine like a command line application where you pass like an input file and it's gonna run a classifier and print the output, for example, the softmax, for example. And then this is what it would look like. So you set up the stage with a given, and then you'd call like pass in the input files like so you can have these parameters, right, in the step name. And here it's pulling from the examples in an outline. And then when you call the when, it's basically calling your application and passing that input file and capturing the output. And then the then step is gonna check the output and see if it's what you expect it to be. And here we can have, for example, in the example, you have all the ground truths you want to test. So if you have a bunch of input images and a bunch of classification outputs you want to verify, you can run this, and you can run this on a on a laptop, for example, or on the target hardware, and results can change. One thing we do, it's not in here, is like you usually have like tolerance, because when you deploy models, maybe it's quantized, it doesn't match exactly. So you would have like more sophisticated steps to actually check for that. This is within some tolerance. I think we're gonna skip this one. Basically, yeah, these are the steps I just described just in Python. I'm gonna talk a little bit about just system level tests. So contrasting with application level, at the system level, really testing a box, like running your software, right? Like some hardware, ideally some flight representative hardware, and you'd have like a test computer running these behave scenarios. In this case, for example, it could be like a workstation or a server or your favorite single board computer. And then, yeah, so it would communicate with your hardware. And then, for example, could be any interface. It could be TCP/IP, be serial connection, CAN bus. We've done all of those. And then your behave tests are gonna, operate those interfaces and check if the behavior is what you expect. And, it would do all the same things, right? So just checking the image classification, for example, or any other type of machine learning payload. So in that case, well, another thing we use, which is very useful, is containerized approach. Because, people have mentioned here in other presentations that usually don't have access to, easily have access to, flight representative hardware. So you can run this on a server, for example, or the workstation using containers. And sometimes you have to simulate things a little bit. Depends on your setup. It might be a little bit of overhead to simulate everything. But if it's just TCP/IP, for example, it's pretty simple. And that helps developers to really iterate more quickly using their laptops. And you can catch a lot of bugs on those containerized tests. So that's very, very helpful in being using that successfully. Yeah, I'll just point out some few differences here. This is what, a system level scenario would look like. At this point, you're usually like sending like a model over a network and loading the model in the payload. You'd like maybe mock an image, like not put image, like maybe you don't have an imager. You have a simulator, so you have a step to do all that. And then you trigger an image capture, and you can check, for example, things like inference time. If you have like a requirement to reach some type of inference time, you can do that here as well. But otherwise, it's pretty similar to the application one. Yeah, just to conclude this, just only have 2 slides left. So basically, yeah, why even do this? I think the key point here is clarity. It really helps you understand what you're testing, what the specification of your system is. And it helps also with requirements verification. You can, yeah, if you can put tags on your scenarios, like if it and link those to requirements. And then, yeah, it helps traceability. You can add coverage more easily. And it really decouples like specification and implementation of whatever you're doing. And it helps team communicate, for example, between, in our case, the AI specialists and like people who are actually deploying things to like a payload or some target flight hardware. Yeah, so this just to conclude, we mentioned like this staged approach to deploy models to flight hardware has helped us quite a bit. I think it's worked well for us as do the experimentation and gradually move to something more consistent that we can get consistent results in hardware. And another thing here is like consistency is basically what you're looking for when you run these tests. Like there's a bigger question in AI where how do you know that the AI is doing what you want to do? For example, if you're detecting an object in an image, is it detecting the right object? So that's one question. That's a bigger question that we don't cover here. And but the other question is once you make sure that in your development environment that's doing what you want, when you deploy that, is that consistent with what you tested? So we're mostly approaching like the second part here with these tests. And then there's a bigger question, like we're not aiming to answer that one. So that's pretty big, at least not for now. So, and yeah, BDD has been a useful tool for us to implement all these things. And that's it, I think. Thank you.
All right, thank you, Becca and Luis. In the interest of time, we'll take one question from Slack here. Caroline asks, it sounded like your model archive has reusability between missions. Is that true? And are your model cards under an XML specification?
I can take that one. So the model archive, we switched actually using S3 for that. So there's a lot of infrastructure that's reusable mission to mission. At the moment, we just use specific buckets for different projects, pretty straightforward. We do also have sort of like a catalog specification in those buckets for tracking whether models have been tested, staged, deployed, other bits of information you need to know. that tends to be mission specific. And then the second part of the question, we don't have a spec for the model cards yet. The model card I showed was created by some of our AI specialists. I have a feeling PowerPoint may have been used to create it. I'm not sure. But the point is it communicates the information that we need. And those model cards are really made not that frequently. It tends to be once at the start of the mission, and then once for every kind of major version update of the model.
All right,
A spec would be nice though.
All right, thank you. Round of applause for Becca and Louise.